to that, it is clear that Dr. Poe's trajectory and his role at the DoD has him uniquely positioned to share his insights on the role of high-performance computing power in helping us address and solve many of the technical problems facing the world today. So hence, without further ado, it is my pleasure, and please join me in welcoming Dr. Poe.
I'm glad to have the opportunity to discuss the It's a green. Okay. So is the mic still on? You can hear. Okay. So, it's a pleasure to be here. I'd like to communicate what I think is an exciting opportunity to do that all of you have to make a huge contribution to society, solving the important technical problems that face us today. So, as mentioned, I'm the Chief Scientist for High Performance Computing in the Defense Department. I'm also leading a program which we call CREATE, Computational Research, Engineering, Acquisition, Tools, and Environments, to help the DoD design ships, airplanes, and antennas. And there's a small note here. The Defense Department is a place with acronyms. You've not only got to have something useful, you've got to be able to sell it. And having a good acronym is an important part of that. And so I thought CREATE actually went well with the focus on innovation. So the High Performance Computing Modernization Program provides supercomputers to the Defense Department for research and engineering. We have 5 large supercomputer centers located at Maui, at the Navy Operations Center in Bay St. Louis, Mississippi, at the Army Corps of Engineers Research Lab in Vicksburg, at the Air Force Research Lab at Wright-Patterson Air Force Base, and at the Army Research Lab in Aberdeen. We also have a high-speed network, high-bandwidth network that connects all of the 300 or so user communities with those supercomputers. And we have a software support for that effort, including the CREATE program. Basically, we provide supercomputers for the Defense Department for solving partial differential equations.
His mic is a little too low for the record.
Oh, okay. So,
He's going to turn it up from down there.
so okay? Okay,
Can you hear?
1, 2, 3, 4?
Good.
Okay.
Thank you.
So we provide supercomputers for solving partial differential equations, things like computational fluid dynamics, structures, electromagnetics, computational chemistry, and we're beginning to serve the engineering community. We don't do cryptography, encryption, knowledge mining, signal processing, and so forth. And we don't do weather forecasting, all of the operational issues. But we do the kinds of science and engineering that are relevant to what you were doing. And it's in general areas we serve a large community, all of these different kinds of disciplines, from computational chemistry to space sciences to environmental quality and so forth. So the opportunity I'm going to talk about that you've got, which is really unique to your generation, is it's a point where if you look at the performance of computers, this is euphemistically termed Moore's law, but it's actually not Moore's law. It's because that was about transistor density on chips. The computing performance, the ability of computers to solve problems in terms of gigaflops per second, or in terms of the number of cores available, has been rising pretty steadily, about a factor of 60 to 70% per year. And the goal is to hit an exascale machine, that's 10 to the 18th floating point operations a second by 2020. We may actually reach this. Now, of course, this is the top 500 list, the biggest machines on the planet. Few engineers, and probably few of you are going to get access to that. Not very many people do. But the important thing is, about 10 years later, this kind of computing capability comes down to something that really is accessible to you. And this 10 to the 15th to 10 to the 18th increase in computer power since the beginning of the invention of computers in the early 40s is really allowing us to do 4 important things that have never been possible before. You can do really accurate calculations, use the algorithms to get accurate answers. You can put all the effects in your codes and applications that are that you know to be important. And you can apply these to large systems like the planet, even a galaxy or the universe. Certainly things like ships and airplanes, cars, all of these sorts of things. And you can get reasonable turnaround time. So you can actually do a lot of parameter studies for this. If you have a big code that takes 1,000 hours to run, you're not going to do, that's 8,000 hours in a year, you're not going to do very many parameter studies. Now we're getting computing capabilities that can really allow you to do this, so you can really get reasonable parameter studies. And you can validate those computer models. And as I mentioned, your workstations are going to be just as powerful as supercomputers if you wait 8 to 12 years. But the key missing link in this is software applications, and that's where most of you are going to come in. The software applications capable of computing, exploiting this kind of computing power are very specific to the problem you're trying to solve. A code that'll calculate protein folding is not the same kind of code that can calculate airplane flying, which is not the same kind of code that can predict the weather. And so these are very different problems. They're very different tools. And that's not too surprising. If you're trying to drive nails into a board to build a house and somebody gives you a screwdriver and a shovel, you really don't have the right tool. So you have to have the right tool to solve the right problem. And it really works in terms of an ecosystem. To make all this work, it really is an ecosystem. It involves sponsors, people that have a problem to solve and are willing to pay for it, the solution to that problem. It involves what we call subject matter experts. So they're people who run the codes, who are trying to solve the problems. And they have to really understand the domain that they're working in. A computational biologist has to understand biology. A civil engineer has to understand civil engineering, even if they're using computing. Of course, you need supercomputers with data storage and access to them. You need networks to reach the supercomputers. You need data to validate the codes, validate your use for that. And of course, you need the software applications. And I'll concentrate more on the software applications. But you need all of this system to do this. Now, as you probably know, but I want to reiterate, high-performance computing is becoming a really ubiquitous tool for research, for engineering, and design, testing. And for all of these areas, I just threw a few examples together. For instance, there's been a big breakthrough in weather prediction. Now they do ensemble averages. They run a code and then a weather prediction code, but they run it for a lot of different conditions. And they combine them all to look at the waves. And so a huge success in this was Hurricane Sandy. Normally hurricanes come up, and if they get this far, they just veer off and dissipate in the North Atlantic. The European medium range weather forecast code showed that Sandy was going to come up and then veer in, okay, to hit New York and New Jersey. And it did that. The European code was the first that predicted this. Everybody said, but that's wrong. And people looked at it again and again, and then pretty soon everybody was able to, converged on that answer. That's exactly what happened. That kind of accuracy 10, 20 years ago did not exist. Okay, you're using tools are turning out to be ubiquitous. Sequencing genes in paleontology, looking at what the genes of, they've got pieces of animals that are 20, 30,000 years old. They're able to look at the gene sequence and look at the ancestry of that. And I've worked in controlled fusion for a long time. We're now able to really calculate energy confinement processes in tokamaks with large supercomputers. Even using it in computational mathematics, trying to solve theorems, which is almost counterintuitive. And in engineering, Goodyear Tire, and I'll talk about this in a little more detail, is now designing tires computationally. And they go into production based on the computational design. At the same time, they're starting to test the final result. But they have such confidence in their projections that they are putting the performance, they are going into production. And even in political science, agent-based techniques are being used to model what populations would do. And finally, analysis of big data. Large experimental facilities now absolutely rely on high-performance computing to really analyze the data. The discovery of the Higgs boson, and there were sort of 50 events out of millions of collisions. How do you find the 50 events that are really the collisions that are really evidence of the Higgs boson out of the millions of events that are there with other processes going on? The only way you were able to do this now is with high-performance computing. And these analyses were done not at Fermi, not at CERN. They were done by groups outside of CERN who shipped the data back and analyzed it. And now they're getting to be virtual as well as experimental research facilities. They're sort of now you can simulate what happens. You used to have to do airplanes and wind tunnels. Now you can simulate them. Research facilities used to be big telescopes, or radio telescopes, optical telescopes. Now we can simulate these kinds of events. Supernova has a group at the University of Chicago who wrote the flash code that's typically used. There are other codes like that around. And these are really, these sort of capabilities are really virtual research facilities, virtual regular experimental facilities, and they have many of the same features. And so you can participate in that. Many people use the flash code and use the airplane model code. They never wrote those codes. They're subject matter experts, and they use them to solve problems. There are a lot of examples, and I'll get into them. And industry is beginning to adopt this. There's the Goodyear story, and I'll go through a little bit of detail of that, how Goodyear does that. But there are also many others. There's a Council on Competitiveness in Washington that featured a lot of this stuff, and it's on their website. Whirlpool, for instance, now does a lot of their design work for, they do appliances for 6 different continents. Well, I can tell you that a refrigerator that'll fit in a Japanese apartment, or a European apartment, or an American house, well, they're very different in size and everything else. They want to manufacture them locally. They want to model them, and what they do is that they model the appliance, including things like what's the equation of state of a shirt running around in a washing machine. And they're able to do this, and then out of the final design comes specifications that go to the manufacturing side and said, you want to order this part, this part, this part, and make these other 2 that are handcrafted, not handcrafted, but manufactured specifically for this application. And so with that, Whirlpool is able to specifically sell and manufacture and sell refrigerators in Japan that are designed for the Japanese market, refrigerators that are designed for the European market in Europe, and refrigerators for the United States in the United States. Another example, General Motors has just launched just dedicated $130 million high-performance computing center for CFD, that's computational fluid dynamics, and crash simulations, as reported in a digital thread. And General Motors has decided that this is a very cost-effective way and a very fast way to design cars, make them more safe and make them more fuel efficient. And so it's an important thing for industries. And of course, a very strong endorsement, last year's Nobel Prize in Chemistry was awarded for computational development of multi-scale models for complex systems. So you can read about it at this website. These distinguished gentlemen received that for work in computational chemistry. So I'll talk about now next an example of a program that I had. Dr. Richard Kendall is in the audience. He's teaching at Wake Forest, but he also serves as a consultant, has been working with us on this project as well. So this has been a sort of an example of a use case, an example of how you can actually set up a program and run it to do something that makes a difference. This is computational research and engineering acquisition tools and environments, again, the acronym. So we identified a need. The Defense Department procures and gets a lot of weapon systems. Now it's at the point where it takes us 20, 25 years to get an airplane in the air. That's far too long. We used to be able to do it in 5. We haven't had a new helicopter in 50 years. The last 3 major ship classes have been basically not very good to disasters, depending on who you point. So we have a real problem there. We need to reduce the time, cost, and risk of designing and developing weapon systems for the Defense Department. So that's the first thing that we identified a need. Then we needed to acquire the key skills to actually do this, and then to get the training, experience, and expertise. And so we went out and identified people in the Defense Department who could actually build these codes, brought in some consultants who understood how the process of making all of this work, and had the requisite skills. And so we put together teams to do this, and we've gotten people to work together on this. So we identified the opportunity to use virtual prototyping to really replace the traditional trial and error methods, where you do design, build, test, fail, design, build, test, fail, design, build, test. And these are all experimental tests where you go out and you have to build a physical object and wait for it to do. You can replace that with a virtual processing, a virtual prototyping scheme based on high-performance computing applications. This is the graph that's developed by Dan Patt at DARPA. The study, what we plotted here, based actually on work results of studies done at MIT, we plotted here with, there's a concept called initial operational capability, which is you're building a new airplane. When is it first able to really operate? And so we plot the year in which that was achieved down here, and we plot the year from the start of the project. How long did it take? Okay, it was about 5 years until 1975. And then it began to linearly rise up until the latest fighter we've got, the Joint Strike Fighter, the F-35, has taken 22 years to get to, 21 years to get to the initial operational capability. The Osprey helicopter vertical lift tilt rotor has taken 24. And it's estimated the next generation bomber or fighter will be more like 30. This is intolerable. By taking this amount of time, the F-22 took 20 years. Okay, during that time, the Soviets had 6 generations of air-to-surface missiles. So there was, the platform was really almost out of date by the time it arrived. We can't do that anymore. We've got to get this time down. Now, if you compare this with commercial aircraft, they're more complex and they're getting there, but they're still down around 6 or 7 years. And automobiles have gotten down to like 3 years. So we've got to figure out a way to get this. We've got to figure out a way to reduce the time that it takes to do this. And so what we're proposing for that is kind of use computational engineering tools to replace and supplement a lot of the tests that go on. The current process is really, we can design, build, test, fix, and iterate. That worked back very well in the beginning of the Industrial Revolution, where systems were reasonably simple. You had a locomotive, you build it, steam engine, and you tinker with it and make it work better. And you can iterate that. Systems now are so large and complex that it takes years to do this kind of iteration experimentally. And in fact, you really can't do it very well. That was to gather the requirements, do the design, do some scale model tests. This is the wind tunnel. Full-scale test, build the airplane. This is a C-130. And then it goes into production. And that's been a very good airplane. It's still in use. But it took a long time to get there. Okay. Goodyear has done a different approach. They have what they call their innovation engine. Design, virtual test, fix, build, and deploy. You get the requirements. You design it on the computer. You do the testing and analyzing on the computer, predict the performance, analyze it, then build a physical product and go to market. That has given Goodyear a huge competitive advantage. To summarize each of those, the basic standard paradigm, design, build, test, takes a long time to get to market. And it converges very, very slowly. If you get halfway through that and you decide, well, I don't really need these other things, or I need another thing, and change again, and the defense business, the requirements change a lot. The world is changing very fast. You're stuck. You can't really respond. You discover design flaws very late in the process, and integration happens very slowly, and it doesn't really work. I mean, very well. But you have to have jet engines on a jet airplane. Okay, and so the group that's designing the airframe, the group that are designing the engines get together and decide on requirements and interfaces, and then they can sort of go their separate ways. And they come back and they discover they've each made assumptions and trade-offs that aren't really compatible. And so there's a whole new systems integration situation that happens. You'd like to be able to do that simultaneously. The Goodyear innovation engine, they were able to reduce the time to market from over 3 years to 9 months. Factor of 4, absolute game changer. They were able to cut their prototype costs, their development costs by 60%. But that was $60 million. The budget, the sales of the company every year, $20 billion a year. Their innovation rate went up from 10 products a year to over 60. What they did in this, there was a second lesson in this, is that they didn't do this by mandating that the development process would change. What they did was to change the design process. So they had successful designs that passed the test. They were solid designs and didn't fail and didn't have to go back and do the iteration. And then the product development found, after a while, people decided we don't need to test this anymore because the last 10 times we tested the new design, this worked, and so why do we do this? And so now they have confidence in this process. They don't test the products until they simultaneously start the final test. At the same time they go into production. Once in a while they stub their toes and they have to go back and reiterate, and work on it and figure out what the code's got wrong. But that happens so infrequently that getting this factor 4 reduction in time to market, the year Goodyear announced this and successfully did. The next year, 2 Japanese tire companies put research labs across the street in Akron, Ohio, from Goodyear. And Goodyear, in their annual report, really refers to this as their innovation engine. So let's look at that in terms of what it does for the DoD. Well, if you've taken systems engineering, you know there are 3 processes: concept development, engineering development, and post-development, where you're into production and deployment. And the Defense Department instantiation of this is called the DoD 5000 process. And it basically calls for getting requirements and then the technology, but you really don't get a prototype, a physical prototype, until after milestone B, and this might be 10 years into a program, and you don't get a full system thing until you're really ready for the production lines. If you're going to have a full-scale airplane, you have the production line to produce that. But if you discover major problems here, you're in real trouble, because you can't really make major changes to the airplane without hundreds of millions to billions of dollars of expense. So by the time, as I point out, by the time physical testing reveals a problem, it's really too late to do things. So what we're trying to do with this is to replace it with a virtual prototyping environment where you build a numerical representation of the platform, and then you do the prediction analysis at every step of the process along the way with high-performance computing applications that our group is developing. And you inject physics into the design. Basically, you don't really believe that the system is going to work until you let the laws of nature intervene. And if you have to do it experimentally, it's way late in the process and leads to a lot of delays. If you have good codes that can capture and put physics early in, then you can get the design right and then shrink the time. The Air Force is doing something kind of called a digital thread, which is they want to start with a digital model, a numerical model of the platform, the airplane, and work it and keep it all through the life of the airplane. Such that in the end, they've got, say, 2,000 airplanes of a particular type out, and they have 2,000, they have data on each of those airplanes. They know where they've been, what their environment has been, what the stresses have been, and so forth. And so they know when they need maintenance, they know when they're going to need to be replaced, and so forth. And this will give them a lot of handle on having the most effective and the least expensive system for the Defense Department. What we're doing is building concentrating on 3 applications: air vehicles, where we're putting together for the Army, Air Force, and Navy, aerodynamics, structural mechanics, control, and propulsion, all in one integrated package. For the ships, we're looking at concept design, as well as concept design for airplanes, and shock vulnerability and hydrodynamics. Assess the hydrodynamics performance of naval vessels, including submarines. And that's the core technical competence of the Navy. And then computational electromagnetics, looking at antenna design for the Navy. Every platform in the military has antennas on it. Tanks look like porcupines. Soldiers are burdened down with as much as 50 to 100 pounds of communication gear. All of it designed kind of after the thaw. And you'd really like to design these things right at the beginning. And we've had Maxwell's equations since 1862. We ought to be able to do this. Just no one has really put the effort in to really make it there. And of course, all of these depend on a mesh, a geometry. And so we're putting together a way of doing this that's CAD neutral, since we can't really tell anybody which CAD system they should be using. CAD neutral, and will allow you to take an antenna design and stick it on your ship and get it right. And the tools will support basically acquisition through the entire process from the beginning of the conceptual design all the way through sustainment. Because really what happens with airplanes and ships is you have them for 30 to 50 years, and the requirements of what they're expected to do change dramatically over that period of time. We still have the B-52. It's one of our better operating planes. It kind of looks superficially like the B-52 that was built in the 50s, but it's actually a much more capable airplane that has been modified, has better electronics on it, has better aerodynamics, has better engines. And so there's continuous maintenance on all of these things. So this is just a few details. I won't go into it in too much detail, but the rapid ship design environment is a way to do all of the things you have, assess all of the parts that go into a ship design with low fidelity algorithms very quickly, and then checked out by high fidelity models once you've got the platform together. It's been used recently to do the analysis of alternatives for the Navy's next amphibious assault ship, and they're doing it for the surface combatant that's being announced to possibly replace the littoral combat ships for that. Similarly, for hydrodynamics, looking at all of these different kinds of systems, one of the things that's being used for is to assess the performance of propellers. All of you have seen, you go out and look at commercial aircraft, you'll notice that the wings have a little thing at the end. The purpose of that is to reduce the vortexes, the trailing vortex, to reduce the turbulence that comes off of those. We're doing the same thing with propellers, and we're assessing this with hydrodynamics. And so you can see the little winglets on the propellers. This reduces the drag, increases performance because it reduces the vortices. It also reduces the vibration level, which is something that submarines really like to do. And then there's the high fidelity code for rotorcraft, where this is the first code that's really been able to do all of these kinds of things for a rotorcraft. We can track the vortices using special numerical techniques, track the vortices that are spread from the rotor tips. You listen to a helicopter going overhead, you hear the whack, 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 whack. That's the vortices going down and striking the fuselage of the helicopter. And we can now calculate that. We can even calculate the downwash as the helicopter comes in and it stirs up all the dust. This is really the first time, and we're using this to look at, for instance, the Air Force, the Army is replacing, has got a program to replace the rotor blades for CH-47 freight helicopter that does a lot of freight. It carries about 20 soldiers and lands. They're replacing that with new rotor blade, the new rotor blade design. They'll give them an extra 2,000 pounds of lift in hover. And this tool is being used for that. Similarly, there's a fixed-wing aircraft code. I won't go into details, but that basically was really for the first time able to do simultaneous calculations of the airflow, the structural response to that, the propulsion effects, and control surfaces. One of the things that was really the dramatic calculation that was just completed They're looking at the A-10 Warthog, and the Army and the Air Force were planning on putting special fins and veins on the front surface because they were getting turbulent air going into the engine. And so we have a model for the engine that includes the turbo machinery in that engine so that you can tell about the effects, because the airflow through the engine was a big important issue. And the discovery was that the proposed veins they were putting on the front didn't do anything. And so they're now going back and looking at what can they do to make something to reduce the amount of turbulence going in. So it's those kind of impacts. Now this is a very challenging business because your challenge is to develop the codes for this, which are, the computing environment is changing and it's getting more and more complex as people try to cope with the end of Moore's law. You have to do multi-scale and multi-physics calculations. This is very tough and requires a really deep understanding of what you're doing. You got to worry about software engineering and software project management. People have to work together effectively. And then you got users out there, and they need support. And so that's a major challenge. And then for the applications people, the people trying to use the codes to do something, we need to market all of this stuff to get the necessary resources together for this, because you've got to convince a sponsor that it's worth their money to put into this, to back this, that they're going to get a better answer that way than they will any other way. And you've got to understand the weaknesses of the applications and the strengths and the whole, not only the applications, but the whole ecosystem. Do you have the computer time? Do you have the network access? Do you have the validation data that can make sure that this code can actually do what you need? And you've got to be suspicious of the whole bit. These applications are not black boxes. If you are a subject matter expert and can't look at answers and really tell what's going on and throw out the ones that look like they're nonsense, you're gonna be in real trouble, because you're gonna design something that's not gonna work. Design an airplane that won't fly. And so you've really got to really know what you're doing and not believe the code and not believe the experiments that you've got until you're really sure that they're there. So it's not just enough to take the code and get an answer. You've got to make sure the answer is right. You've got to validate it with a problem of interest, and you've got to reach point. And then you've got to market those conclusions to decision makers. So you've got to be able to convince them that what you've done is right. So it's a lot more complicated and responsible than just a simple system. And of course, there's another major challenge, and this computer complexity is growing like crazy. This is from the National Academy study, Future of Computing Performance, announced in 2010. This shows that around 2005, the clock rate for processors sort of ceased to really grow again. This is called the end of Moore's law, but it's really not Moore's law. It's really the power limit. At that point, the heating of the chips, it got to be so large that the power consumption on the chips was getting to be enormous, and they were getting too hot. You couldn't cool them. And so clock rates are really sort of pegged at about 2 gigahertz. You can run some of them up to 3 or 4, but not. You can't keep doing that. Okay, and so so really you're looking at situations where massive parallelization and special purpose processors are really in the future. We've got to figure out a way to do this, and the next generation of computers is going to need new applications, and basically almost all the legacy applications we've got have to be rewritten, so that's a huge challenge as well. And then from the sort of cultural anthropology side, there are really two kinds of applications out there. There's one where the developers and the users are one the same or two different. Okay, and this is really the historical one, where the code developers were often the major users. You went out to your research, you wrote your code, and you had a lot of tacit knowledge about that code. You knew, because you'd written it, that it really was completely useless for this whole class of problems out there, even though it maybe could have been. And yes, it was useful for these problems, but only in certain circumstances. You understood the strengths and weaknesses fairly well. Well, if you give the code to someone else, they don't have that tacit knowledge, and so they have the potential to really get a lot of silly answers, and somebody would believe them. So you've really got to be very, very skeptical about all of this. These codes are also not designed for general use. They're validated for the purpose that you're looking at, but not for other things. They're kind of hard to use and minimal documentation for academic codes. This would be my standard complaint about, everybody's standard complaint about academic codes were developed as research things. But it's a business model issue. Graduate students and postdocs, they're not motivated to write an industrial strength code that users can use reliably and robustly. You know, they want to get a paper to get the postdoc get a paper to get their next job. The graduate student wants to do the research, write it up, and get out. And neither one of those emphasize software engineering and software quality very much. Okay, they're you know, that's natural selection because if they don't, they never get out. But there are now a lot of codes that are written where the users and developers are not the same group. And there are lots of examples. I have a few listed here. And this is the paradigm that's moving. There's still a lot of these codes, okay, but there's a lot of these codes too. And they have a different sociology. If you're having a successful project to do this, and you have some flexibility, a code you develop yourself can always be successful, or pretty much always, because you can always write a paper, you can always find some application. An engineer trying to design a ship hasn't got that freedom. You know, that engineer has to produce a study and results to solve that problem, and so they can't go off and write a paper about, you know, this did a great job or something else. And the development of these codes, particularly for use by others, takes a lot of time, like 10 years or so, the case studies that we've done, and it takes a multidisciplinary team, which are longer and larger than pure research codes. And these are the kinds of things that have been used for that. And they have more, as I said, more stringent criteria for success. They have to be adopted, and the users have to have confidence in them. And they have to have support, which is not an academic sort of thing. And it's a lot harder. If you look at the evidence for that, there's a lot of examples where they didn't really, people wrote the codes and they really didn't get adoption for a variety of reasons. And in fact, there's some spectacular examples, not necessarily in science and engineering, where large complex software projects really failed at the $100 million to $2 billion level. The NSA spent over $2 billion on Trailblazer and never got a line of executable code out of that. So there are a lot of scientific challenges there. This will be posted. I won't go through these in detail, but you have to validate these things. You have to build the meshes to do this. You have to be able to analyze the results that get out. And in the project side, you have to form a small team to a regional sized team, multidisciplinary people who are not co-located, who can work together and make a big code like this. And you have to support it when you're through. And of course, the programming environment is going to be very challenging in this. Computer architectures, you're writing codes. If you're doing this for engineering purposes or some research facility purposes, you're writing codes for computers that don't exist yet. And so you've got to be pretty astute to figure out where the community and what features you build into your code that will survive 10 years of changes in the architecture of computers. And you have to get good performance out of them and develop these codes and run massively parallel applications with extremely immature tools. The tools are being developed if any of you tried to use the latest compilers for general graphics processing units, you have a good sense of what we're talking about. CUDA is not a very user-friendly language. It's still being developed, as a matter of fact, and so not very mature. And especially the research communities have very limited experience developing these kinds of things. You have to pay attention to the appropriate processes for doing this, software engineering processes and practices specifically designed for this kind of purpose. Your success is measured by basically the number of users and the impact, longevity, and that. And you need funds for doing this, and this is turning out to be a real challenge because while decision makers appreciate the need to, for a wind tunnel, for instance, to modernize the wind tunnel, pay the electric bills, support the staff, and so forth, they don't appreciate the need to maintain a group of developers working on a code. And they give up, and then they're very surprised when they come back 3 or 4 years later and discover there's nobody who understands the code anymore. So it sort of dies, and they don't understand that it has to be supported just like a standard, just like a regular facility. This is the evidence that it really takes. This is the case study that Richard and I did at Los Alamos of a code. It takes about 10 years to build them. It takes about, and they have a life of maybe 20, 25, 30 years. And then eventually they get kind of long in the tooth and they die off. But some codes last, Nastran's been around since 1970, so it's approaching 45 years. It's a commercial code, but it was originally developed by NASA. It's the NASA. So these are long-lived things. There are a lot of other challenges. Multi-physics to integrate all of the important effects. This is a slide I took from Pratt & Whitney, but it shows you all of the things that go into a jet engine model for that. The fan blades, the turbine, the heat transport in the turbines, the structure mechanics associated with the fan blade, being able to calculate the flow of air and fuel through the turbine, and the combustion, which is what drives it. You have to have fuel air, and then it has to evaporate and mix, and then it has to burn, and you have to calculate the physics of that. And you have to balance it, of course, across all of these things, such that you're able to do that computation as an integrated one. And it has enormous value in this. And Pratt & Whitney uses this. There's another concept which I put a slide in because one of my colleagues wanted. He said, people do not understand this whole issue about hierarchical fidelity. And so it's really, so I thought about an example that I could use for this, and I decided on the capsule. It's the Consortium for Advanced Simulation Light Water Reactors. It's being run out of Oak Ridge. And what they're doing is to put together multi-physics models for designing nuclear reactors. And there's a lot of information at capsule.gov. And so what are they doing for, that's a good example of a multi-physics, hierarchical fidelity. What you're really looking at is your design goal is to have, in a steady state, that what's driving this is a chain reaction. You've got fission, it produces a neutron, that neutron goes off and causes another chain reaction, and so it causes another fission event. And what you'd like to do is to keep the fission rate minus the leakage the same, because of course you have collisions and fission, and then some of the neutrons leak out in some state of the system and cause more fission. And so it's a chain reaction, but you want to have this very close to zero. If it's less than zero, of course, the reaction goes out, the power plant shuts down. If it's greater than zero, well, the big example of that is an atomic bomb. And so you don't want that either. So you want the thing to balance very well. Well, this is a hard calculation. It's called criticality. And it's in a very complex geometry. Here's the reactor core. It's got a lot of fuel rods. It's got control rods. It's got all sorts of structures. And so this is kind of very complicated. And so if you really want to do this accurately, it's a very complex calculation. So what you really want to do is a good trade-off between accuracy and computational cost. Time to solution is really a question. If you're a design engineer, you really have to worry about time to solution. You're expected to come up with an answer for a design decision in a certain period of time, like say 5 or 6 months. And you have to make that window. So you have to look and see what you can do within that. Do this, and so what you really want, the time that is really the turnaround time times the number of runs you're going to make. Okay, and so you also have to know that highly accurate runs take a long time. So you can't do very many of those. So you're going to have to use lower accuracy ones that have low turnaround times and can get answers very shortly. So you want to do many low fidelity runs to quickly identify the design points you want, and you want to check those for the high fidelity runs. And so this is an example of this. This is the algorithm, time to solution, geometric fidelity, and that. So if you want a low fidelity, you can do get things very quickly. As you move up, a difference the diffusion equation for the neutrons, which doesn't really do a good job of geometry, but it gives you kind of a scaling mark on it. And then you can difference the transport equation itself in discrete ordinates, and that's kind of medium. And these are examples of codes like that. And then a highly accurate one, a Monte Carlo technique, can do a very good job of the geometry, but requires a lot of computer time. And one of the reasons for that is, of course, the error rate for Monte Carlo calculations is proportional to 1 over the square root of the number of samples, number of events you've got, which is really the square root of the time of solution. And that's a very expensive way to do it. But you do it at the end because that can capture the geometric fidelity. Another challenge is the multi-scale. Going from the atomic to the macro scale presents challenges. Avogadro's number is a big number, okay, as everybody knows. And so if you're looking at it, the atoms are really sort of separated by an angstrom, and that's just a simple dimensional algebra. 10 to the 24 atoms in a cubic centimeter, and then you take the cube root. And so the atoms are at 10 to the minus 8 centimeters, and macroscopic scales count as centimeters or millimeters. The scale doesn't really matter. So if you want to look at fracture growth, model materials, okay, you're looking at the atomistic scale, which is this is 15 angstroms, okay. But you're really looking at crack growth in the macroscopic scale. This is a millimeter, 10th of a centimeter, and so that's a huge difference. And you can't do this with brute force techniques. There just isn't enough computer time. And so, of course, as I mentioned, large codes fail regularly. So how do you address those challenges? One is you use really good, solid software engineering techniques with a fanatic attention to verification, validation, uncertainty quantification. There's a National Academy study that recently came out on best practices for science-based code. And you need to reduce the problem scale. We had a discussion about this with the people now. How do you, high dimensionality is expensive, requires accuracy. You need to reduce the dimensionality and reduce the number of entities in your problem. And I'll skip the characteristics of reductionism and emergence. It's contained in Bob Laughlin's paper, which I've passed out and is available from the Computing and Science Engineering in this. And so there's a lot of examples of successes in this. GAINS, the computational chemistry code, is a standard of the field. If you've done computational chemistry, it's there. CAT is an astrophysics code, University of Chicago. And they're the CREATE codes that I described. It does all of these sorts of things. And the metrics is really the number of users, impact, publications, longevity, the financial support you're able to get out of that. And so to really conclude this, you have a huge opportunity here. This is an emerging, a really very, very powerful program, paradigm for solving important problems. And you're the generation that's going to do this. This is really the first time we have the computing power to do this. It requires the software applications and the people to run them and solve the real problems. And so that's really your opportunity. It's a huge workforce enhancer, productivity enhancer for you. You can do a lot more than people who are trying to do things with pencil and paper, or people who are doing things experimentally, because it doesn't take so much time to build an experiment and to do the tests. And you don't have to travel to where the big experimental thing. And a place like, it's also very distributed. You can do all of this starting with a laptop using a supercomputer somewhere else. You don't need to, NCAT doesn't need to set up a huge accelerator or a huge telescope or a huge industrial facility. You can tap into the computing resources the NSF has, the Department of Energy has, NOAA has, NASA has, all of these, and the Department of Defense do this. And these tools actually are useful for a lot of different things. You have a computational fluid dynamics code. You can calculate airflow, the resistance of a car or of a ship or of an airplane. These tools are really very applicable. And that's because the laws of physics are applicable to everything. And the tools are reasonably flexible. But you have to get ready for this. Okay, this requires opportunities, skills, and hard work. You need to identify a need and an opportunity for you to solve an important problem, and then be prepared. Prepare yourself to take advantage of that. And you need to require the specific skills to do this, training, experience, to really exploit these kinds of opportunities. And you need to be a subject matter expert in something. If you've learned to speak French, that's very good. But what are you going to say? You've got to have something to say in French. And it's just like that with these things. You've got to solve physics problems. You've got to understand the physics, or chemistry, or biology, materials. You've got to be able to know what's going on in that. And you need a strong background in mathematics. I can't stress enough the importance of mathematics. I know a lot of engineers who said they didn't really appreciate the need for mathematics until they were graduate students. And then it was kind of too late to go back and require that background. And so they sort of, but they would then, and of course you're using computers, so that's a craft. You've got to understand the craft of how to do this. And you've got to work hard and stay focused to solve the problem, to do this. And these skills in physics-based computational science engineering are really applicable to almost all of the problem. So, are there any questions?
Before we open the floor to questions, I know that some people may have a class that's about to start in about 5 minutes. So if you do, I understand that you have to leave. Just want to tell you that's why I'm leaving. But yes, let's open it up. And John, and then
All right. Thank you very much for a great talk. I have two basic questions. Is it still Fortran or is it C++?
Yes.
Okay. Yes. So it's still Fortran.
it's both.
It's both.
All right.
That's actually one of the tragedies. There is no good language for massively parallel high-performance computing. And but that's a challenge. If somebody can really write something like that and then get it adopted, that would be very good. But Fortran is evolving. What's tended to happen is the languages evolve. And so, you know, Fortran is, somebody used to make a joke about, they don't know what language they'll be using in 20 years, but it's going to be called Fortran.
Yes. And the other question has to do with the number of bits. 10 years ago, we used to have 128 bits. In the hardware, but now the chips that are being produced are only 64-bit. Aren't we going backwards?
I don't know. I think there's still double precision chips are being produced, but I don't actually. I'm trying to think of what I know about that.
There used to be
64 bits are, you know, that's how many bytes? That's 8 bytes. So but it's 64 bits as opposed to 32 bit.
Yeah, digital equipment used to come up with a standard bit chip which had 128 bytes per word, but it was bought by Intel and then killed.
Okay, well. There's enough accuracy in the things. You just go to double precision. I don't know that much.
My question has to do with human system integration. And you gave some interesting cases about General Motors going towards agility and such things. Back in 1996, Miller Brewing Company.
What company?
Miller Brewing, they do beer.
Yeah, okay, yeah.
They produce beer. Now, they try to use high-performance computing on the electronic eye, which is the camera for inspection of foreign objects on the bottle as opposed to.
Right.
Beautiful. The line was good. Sharp. However, when the humans are looking at the FAA approval of foreign objects in beer, there were more rejects from the camera, the high-speed camera than the human. So, given this high-performance computing, mostly physically based, at what boundary do we have to really apply it in order to achieve a successfully engineered system? That's question number one. Question number two, based on what is happening with General Motors, it's testifying in Congress right now. Is that a part, the threat coming from computational or human design?
Well, I mean, this is not a panacea. This will not solve all of mankind's problems. So it can solve it can enhance your ability to handle technical issues. And so, but there's absolutely no way you can eliminate stupidity or human failings with this. I mean, the problem with the General Motors thing was that it's a business decision, and they decided it was less trouble and less expensive to fix as I understand, $1 part than it was to this. That's not a. You don't need high performance computing to figure that out. Okay. What is it? I would say if there's anything that high performance computing is really sort of a court of last resort. You use it for problems you can't fix any other way. If there are problems you can, and I think they could identify the problem with the ignition switch without recourse to high performance computing.
Yeah, so I have a question regarding one of the comments that you made about the researchers who normally work or contribute in the developer side. So don't you think it's expected, because most of the time developers or the researchers, they work on understanding the fundamental physics associated with these issues. For example, when we do multiphysics, from atomistic scale to macro scale, the transition itself is so hard to understand the physics.
Right.
So most of the time, developer, it's kind of expected that we don't really bother about getting high fidelity or high performance really, because just to understand the physics and model it into a computational background is the grand challenge.
Right. Yes.
So, but then when I look from my career that if I try to implement to a large scale, usable product, maybe in the manufacturing side or in some other, let's say some existing software wants to buy my product, then real issues comes that my code is not having high fidelity. So how do we actually get transition from this fundamental research to this? Because I feel as a researcher, we do have limitations about time and understanding the problem. Someone else from outside has to make the leap.
That's the way most of the time it happens. But then that person is got to have a business case.
Right.
There's got to be a market for whatever tool you're putting together. And it's got to have adequate fidelity to address the problem that your customers might have. And then if you have a lot of customers out there who didn't write the tool, it's a whole different set of requirements for what the tool looks like. It has to be documented. It has to have a reasonable interface. It has to have a lot of checks on the input. I mean, if you're running a code and you pretty much know what data the code would be happy with and what data you would never put in it because you're going to get nonsense. Or even worse, you're going to get very misleading answers. And so you wouldn't do this. But the user out there in the commercial sense, person marketing the code to a bunch of other people, like graduate students, your competitors, competing universities, like Gaussian would be something in your area. That's a wholly different kind of enterprise. That you have to build a lot of quality into the code and documentation so people know it and understand and can read about the limitations. And then you've got to look at it and put some warnings in the input that say you put data in it that's not really compatible or going to mislead. And you have to tell the users, because to some extent you're a partner in the crime if they end up getting the wrong answer and publishing it. So there's nothing easy. There's no royal road to code development. Just to paraphrase Descartes, there's no royal road to geometry. You have to deal with all of these problems. It's just not easy. But in fact, paradigm shifts themselves, which this really is, high performance computing applications to really solve hard problems, to supplement testing and theory. The paradigm shifts are never easy. In fact, there's a great quote from Machiavelli about putting the prince, putting things, establishing paradigm changes is usually very, very hard, because the people who are doing things the old way will attack you vigorously because you're trying to put them out of business, or they see it that way, and they probably are right in many cases. And the people who tend to benefit from the new paradigm are kind of weak advocates for this because it's a lot of trouble and so forth. And I don't have exactly, in one of my slide decks I have a quotation from Machiavelli, but that's really the point. So this is not easy, but the opportunity to really change the way science and engineering is done in this country and in the world is really is a huge opportunity.
So to connect to that, when you were talking about the mesh geometry generation and create,
Yeah.
you mentioned that it had to be CAD neutral.
Right.
But there's no standards that exist when you talk about Nastran versus Abacus versus Ansys, etc.
Yes.
So with that in mind, what are the anchors that make it CAD neutral that allow, when Dr. Singh is designing, for her to make sure she puts those parts in her code to allow the neutrality to exist?
So by neutrality, what we're doing is putting together a numerical representation of the geometry of the system. So that's a NURBS-based. That's a system that's based on spline representations for the points, and from that you can build a mesh. Okay, and so what we're doing is starting from the geometry and building the mesh, and then do the analysis on the mesh, and get the lessons learned, like you're doing a CFD analysis of the lift and drag on a wing or something like that. Then what do you want to do with the wing? You want to change the camber a little bit. Okay, don't go back and reverse engineer the mesh. Go back and change the geometry a little bit, and then generate the mesh again. That's a process that can be automated, and you can generate. So we have tools for generating the mesh, or generating the geometry, and then moving to the mesh. And then we can have them in the geometry, you can put them together and merge them. And so we can use the standard CAD tools to get a first cut at generating the geometry. And then we have ways of turning, develop tools to take that and to repair it, because generally when you do that process, you get a pretty imperfect pretty imperfect representation of geometry with gaps, and it's not watertight and lots of other things like that. So, but that's because we were really interested in being interoperable, being able to put an antenna onto a ship, or being able to put a mesh together where we're having an airplane land on the ship, which is something we do with the Navy a lot, and then also put antennas on things like tanks and airplanes and ships. So that's the reason we're doing this. Otherwise, we would just be in an incredible, it takes, when we started, it took a year to mesh up an aircraft carrier. Now we can do it in about a month. That's a huge improvement in the productivity of the process.
Any other questions?
What's the difference between grid computing and high performance computing? I mean, the fundamental difference, and then in terms of the applications. Grid computing.
Grid?
Grid.
Spelling.
GRID.
That's kind of like cloud, or I'm not sure.
I think it would be more cloud, right?
Cloud computing.
So there's, I've been in this business for 40 years. Okay, and so I've since learned that you have to be very agile in your vocabulary. And so I now know to call what we were doing in the 60s cloud computing, because we had a computer that you linked in from the, came in through a network, and sitting in your lab in Princeton, you could log into the computer at the National Supercomputing Center for fusion work, and run your problem and get the results back and that sort of thing. And your results, your code was stored there, you developed it there. And so that was a cloud computer. And then they had the computer center, the Fusion Computer Center at Livermore had then 4 7600s, and you could use one or the other, it didn't really matter. Well, that was a cloud, okay, so that's the way things were done. So, but now, cloud is a little more than that, I know that, but it's a little more accessible, but it's kind of the same idea. And it's time sharing. So grid computing is high performance computing is it's usually you can have high performance computing, just one computer sitting in your room. Well, it'd be kind of a warm room, probably if it's a big machine, but That's maybe not grid, that you're using it yourself, or it could be some distributed set of computers like the ones we have, the NSF has, the Department of Energy has, at big computer centers with the big computers, and then you come in through the internet, or local networks, specific networks that your institution or the funding agency the agency you're working with has. So, does that really address your question?
Maybe, because I'm asking that because I mean, in grid computing, you could grapify the codes. So that means you could have the codes in chunks running on several machines. And then what it is that, I mean, depending on what you need to do, you can harness the computing power of different machines. And at the end of the day, they all.
So that's kind of
Parallel.
anyway. This is software-oriented architectures, where you have one code sort of running services, and you get it from another computer. That tends not to be so much in the high-performance computing business, because there you're interested in very low latency things. And if you have to go off the machine, let alone off the chip, you got to wait a long time for the information to come back. And so, what?
It is problem dependent. Depending upon the problem, you can either use grid computing or high performance computing.
Yeah.
Some of the things you talked about, grid computing is not going to be good because of the latency.
Right. So the real example of that, I guess, is maybe I'll date myself. Remember, at some point, everybody's machine was SETI was going out and doing things, and so they were running this thing among millions of people's computers. I thought it was a security nightmare. I would never let anybody put stuff on my computer, because who knows what, back then people were more trusting and there weren't so many malware things out there. But now, you open your computer up and you discover everything.
So in the interest of time, there is a reception hosted by the Computational Science and Engineering Department in the faculty lounge, one floor up over there. And so we'll just join me and thank you, Dr. Post, for his seminar.